All right, so on this question, kind of a long question about bicycling. You know, I love bicycling, so this is kind of cool. But we have, they're basically saying that the force is proportional to the square of the velocity, which is true. And we're going to say it's exact. That's an important thing. So we've got a cyclist, and she's riding her bicycle. We know her mass, and we know what her speed is. So if we have a drag force of the cyclist, how much energy does she use? Remember, energy is energy is energy. But in this case, what we've got is we've got a force and we've got a distance. So work is force times distance. I bet you can figure out how much work that's done. The 5 meters per second will come in play later, as will the mass. So the drag force, because that's how much energy she has to use to cycle, because she has to overcome the drag force, assuming she moves at a constant. It kind of says that constant 5 meters per second. Now, how much power does she expend as she cycles? Well, what is power, right? Power is work over time, or energy over time. And so we have information about this. We need to find time. Now, we know some information. What do we know? We know that she's traveling at 5 meters per second, and we know that she traveled for 3 kilometers. So, of course, velocity is distance over time. So solve for time and plug that into the power equation. Sorry. Question C here, if she doubles her speed, this is where it gets a little tricky. How much energy does she use cycling 1 kilometer? I messed that one up. It took me a minute to figure that out. First of all, you can still also use, you're going to need time later on. So solve for the time, 1 kilometer, 10 meters per second. Solve for the time. That'll come in useful in a minute. Now, what she's done is she went from 5 to 10 meters per second. So she doubled, right, her speed. And if you double the speed, think of like V1 is 1 and V2 is 2. It makes way better sense to do it this way. So what's happened is she's increased her force by 2 squared, or 4 times. So instead of a force of 20 newtons, her force will be 80 newtons, right? And if you know that's 80 newtons, you can solve for the power. How much energy? That's it. Yeah, work is force times distance. Now note here, it's over 1 kilometer. That's where I messed up when I was doing the problem. 1 kilometer. How much power does she expend? That's where we're going to need the time from this one, right? 10 meters per second, etc. Now, we then reduce our speed, but then she discovers she has a headwind. The last question. So if she's moving at 5 meters per second, but she has a headwind, right? So she has to basically be traveling, or she's got to be pushing at 10 meters per second. 10 meters per second, the force has to be quadrupled. So it's really kind of similar to the last question. All right, and so what you want to do is, how much power is she expending now? What did I do? I had to say, you're still going to have 80 joules, right? And you can divide by the seconds, and you can get the wattage. So, yeah. So it's, actually, no, that's not how I did it. I said, if you have your force will be 80 newtons, but now that we only have 5 meters per second, remember there's also the equation, power is equal to force times velocity. I know what the force is, 80, and I know what the velocity is, 5, and I can solve for P.